So welcome everybody to the Rocky Mountain Mathematical Physics Seminar. Today we have Howie Jordan as our speaker. He's from the University of Colorado and will speak about the Sheaf Theoretic approach to contextuality in quantum mechanics. Please, Howie.
Thank you, Marcus. Yes, so as Marcus said, I'm going to be talking about contextuality in quantum mechanics using sheaves. Okay, but first, some historical background. So in 1935, we get this paper by Einstein, Podolsky, and Rosen, where they argue that quantum mechanics is necessarily an incomplete theory. They propose that there should be some sort of, in principle, hidden parameters that determine the measurements that we witness in quantum mechanics, as opposed to the traditional formalism that's entirely probabilistic in its predictions. Okay? And at the time, there was some work due to von Neumann that argued that this wasn't the case, but not everyone considered that entirely satisfactory because of all the conditions that von Neumann assumed in his proof to show that there was no such hidden variable model, so to speak. Okay? But then in the 1960s, really 1964, 1965, we get a couple of proofs in the negative, one by Kochen-Specker and another one at around the same time by Bell. And they demonstrate that there is an inherent contradiction between the following three principles. First, that all of the observables defined in a quantum mechanical system have definite values. Second, and this is the most important one for my talk today, that the values assigned are independent of the measurement context. And I'll just say context, but I really mean measurement context. And lastly, that the projection operators correspond one-to-one with the properties of a quantum mechanical system. Okay. So what this tells us is that any approach to quantum mechanics cannot simultaneously have all three of these conditions met. And so any alternative approach necessarily violates one of these. And sort of the most common one to consider violating is this middle one, which I'll call noncontextuality, or NC for short. There are approaches that consider the other two, but today I'm only really going to be considering noncontextuality. Okay. So that's our historical setup. But before I jump into the Kochen-Specker result, let me actually give a precise definition for what I meant by quantum mechanical observables on that last slide. Okay. So what I mean is, given a Hilbert space corresponding to some quantum mechanical system, okay, by the observables I mean the self-adjoint elements of B of H, the bounded linear functionals. Okay. Yeah, okay. So that's my formal definition here of what I mean when I talk about a quantum mechanical observable. And I should say, you know, I'm using specifically B of H here, and that's mainly what I'm going to focus on. If we're doing a general C-star algebraic approach, we would just say the self-adjoint elements in whichever algebra is relevant. Okay, so here's the Kochen-Specker theorem as it was originally presented. We'll say Kochen-Specker, we'll also say Bell. It was really about the same time, and often it's just called the Bell-Cochen-Specker theorem. Okay, so let's let H be a Hilbert space with dimension at least 3. Okay, in that case, we have a set of observables. I'll call it M. So a set of self-adjoint elements of BH, a set of Hermitian matrices, such that the following are contradictory. Okay. The following two things can't hold. First, we might want all elements, I'll just call them little a and M, to have a definite value. We'll say that that value is V of A. Okay? And moreover, I really want that value to be in the spectrum. This is our usual idea that we take one of these self-adjoint elements and we apply it to some state. And if that's an eigenstate, the corresponding eigenvalue is the measured observation. So we want to say, okay, well, do all of these elements have a definite such value at once? And whenever we do have those values, and whenever we have two observables that commute, so they're in a sense compatible observables, they don't, if they don't commute, then the idea is if we measure one and then measure the other, it's different than measuring them the other way around. If they commute, the idea is they don't affect each other, they're compatible observations. We don't have, say, uncertainty to worry about. Okay? So whenever they commute, we might ask that the value of their product is the product of the values, and same thing for the sum. And this right here, the second condition, this is where most people ran into issues with von Neumann's original result, because von Neumann assumed these two principles holding for every two observable, regardless of whether or not they commuted. And most people rightly pointed out at the time, and von Neumann himself knew, that this was definitely not the case, that would hold for non-commuting observables. And it's pretty easy to see this even in, say, like a spin 1/2 system on C2. You can just take a couple of different observables and you can check that that's just in general not going to hold. Okay, but this Kochen-Specker result is in that sense a bit of a weakening. It doesn't require quite as many stipulations, but we're still able to show the same no-go result. Okay, so I'm going to give a quick sketch of the proof. But first, a couple quick notes. First of all, it suffices to just consider projections. We don't have to consider every self-adjoint at once, actually. We can just consider the projections essentially just because of the spectral theorem. If I have a self-adjoint element, I can decompose it as projections onto states spanned by, or projections onto closed subspaces spanned by different eigenstates and eigenvalues times those projections. So it suffices to consider the projections. Okay. Orthogonal projections always commute because PQ equal QP equals 0 for any two projections that are orthogonal. That's just the definition of orthogonality. So they, of course, commute. Okay. And for all of these projections, the only values they're going to be allowed to take are 0 and 1. Those are the only two eigenvalues. We want everything to land in the spectrum. So those are all we're going to allow this valuation to assign. And so, in particular, whenever VPQ equals 0, right, that's just V of P times V of Q by our requirement that this respects multiplication on commuting operators. So that's going to tell me that, of course, either VP must be 0 or VQ must be 0. So whenever I have orthogonal projections, I necessarily am assigning one of them 0. And that actually extends a little bit. So for any family of mutually orthogonal projections, the same thing is true. And in fact, we can see, maybe I'll just call them P1 through Pn, that V of the sum of them has to be 0, or has to be exactly 1 or 0. Either they're all assigned 0, in which case the sum is 0, or at most one of them is assigned 1. Okay. So those are just some quick notes to kind of justify how we're going to consider this theorem. And I'll note that the original proof that Kochen-Specker did was in 3 dimensions. I stated the theorem is requiring at least 3 dimensions. The original proof uses 117 rays in 3D space, and the projections onto the subspaces spanned by those rays. I'm not going to do that. I'm also not going to consider a slightly easier method, but I am going to note that you can actually bring this down now. There's been lots of research into minimizing the number of rays you need. And in 3 dimensions, I believe this is down as low as 33. I don't think it's any lower than that, but that's due to Perez, I think in the last 20 years or so. Okay. I am going to consider a nice, easy 4-dimensional example, though. This is a very common one, because this one only uses 18 rays. Okay. Originally, I had a chart already with all of the 18 vectors that I was going to consider. And I don't think it would be very prudent of me to rewrite all of those, given the technical issues. So instead, I'm just going to sketch out what happens here. So what happens is we take 18 projections, we group them into 9 groups of 4. So I'm just going to use my squares here to do my grouping. Okay. And I group them in such a way, maybe I can fill this in while I'm talking. I group them in such a way that each vector appears twice in this table in 2 different columns. Maybe I'll just fill in a few here just to kind of show what I mean. So for example, this first vector here, 0, 0, 0, 1, I put it in 2 different columns, but other than that, the columns are different. And so I've got this one, this one, this one, this one, and these last 2. Okay, I'm not going to fill in the rest of the table though. So each of these is really a 4-tuple, and we want to imagine this as representing a projection onto the corresponding span of that 1-dimensional ray. Okay, and then just imagine the rest of the table is filled in and that each vector appears twice. Okay, so let me just note that. We group the rays into sets of 4. And I set them up so that each set of 4 is mutually orthogonal, and each ray appears twice. And if you're curious to see the rest of the table, if you Googled 18 vector Kochen-Specker proof, you'll find this chart all over the place. Okay. So if we wanted to have a valuation function that satisfies the conditions that we laid out, all of these columns here are going to be my mutually orthogonal groups of projections. So this column here is a group of 4 mutually orthogonal, this one is, and so on. Okay. Well, since they're all mutually orthogonal, I can assign at most one of them the value 1 via my valuation, and the rest in that column have to be 0. Okay. So let's note that. I've got 9 columns. They're mutually orthogonal. So if I wanted to maybe put a 1 in every column, I'm going to have 9 1s. Okay? But I have put each ray in 2 different columns. So since each ray appears twice, and I want these values to be determined, definite for all cases, then I want to assign, for example, if I want to assign a 1 here and fill this in with zeros, this vector over here is the same vector really, so it also has to be a 1, and zeros have to be going down the rest of that column. So every 1 I have has to have a matching 1, so there must be an even number of 1s. And so there's immediately a contradiction. I can't put a 1 in every single column in a way that respects my valuation rules. So that's a pretty simple little proof. It's like an easy little counting argument. So we know that there does not exist such a global assignment. Let me erase that and say this a little differently. Okay. There does not exist such a valuation. Of course, I've only really shown that it holds in 4D, but as I said, there's proofs in 3D too. They're just a little bit more complicated, but the same basic analysis holds. Okay. So, not going to fill in that box. We didn't prove everything. We'll just give it a square. Now, this is interesting because for a commutative unital C-star algebra, we actually do always have valuations. We just saw that in B of H we don't, but for any commutative unital C-star algebra, they do exist. What are they? Well, they're exactly the characters of that unital C-star algebra. So any character, A to C, a character is a non-zero star homomorphism. Okay. Any character gives a valuation by just restricting to the self-adjoint elements, right? If I just take V and I restrict it down to the self-adjoint elements, I land in R, and I'm a star homomorphism. Everything's commuting. I'm meeting the exact conditions I laid out in my Kochen-Specker theorem. Okay, and conversely, any valuation on such an A can be extended to a character by just taking my decomposition of A into its self-adjoint part, and I suppose we would say its imaginary part, I times its self-adjoint part, okay, by just extending linearly. Okay, so for any commutative unital C-star algebra, I'll just write commutative C-star algebra, the Gelfand spectrum, that is the set of all the characters, is the set of valuations. Okay, so I'm going to use the capital sigma for this Gelfand spectrum, and it just assigns all lambda such that, let me go ahead and say that that's a lambda from A to C, such that lambda is a character, a non-zero star hom. Okay, so the Gelfand spectrum is the set of valuations. Okay, so what we've seen is that locally, by which I mean commutative subalgebra wise, valuations do exist. Oh, that's looking weird down there. Cool. Well, hopefully that's still readable. Okay, so locally valuations do exist, but globally they can fail to exist. And this suggests a reformulation in the language of Presheaves and Sheaves, because Presheaves and Sheaves are naturally an organizing strategy for considering a bunch of data defined locally and trying to ask the question of whether or not that extends to a global assignment. Okay. So this suggests the following reformulation. Okay. So what we do is we consider all of the commutative subalgebras of a given C-star algebra all at once. So for a C-star algebra, and I'll go ahead and make it unital. I don't really care about the non-unital case today. I'll denote by con of A. We'll let that be the set of commutative subalgebras. Okay. And they're going to be ordered by inclusion. So note that that gives me a poset, which is nice because a poset is really a special type of category. And so this lets me further define Presheaves on this category of context. Okay, so I'll call that the context category. Now, a Presheaf on this context category, I'm just going to give it in the case of being on sets, but later on we might consider algebraic structures there. Okay, a Presheaf on this context category is, well, it's a contravariant functor, but let me spell out what that means here. So what that really means is for each commutative subalgebra, and I'm going to be denoting those V. So for each V, I want a set, and I'm going to denote that set P sub V, where P is my Presheaf. And for each inclusion of sets, or of subalgebras, I mean, I want to have a restriction map that goes from P of V, my larger subalgebra, to my smaller one. So that's where the contravariance comes in. My inclusions I think of as going from V prime to V, but my restrictions go the other way. And for this to be a functor, I need to have some respecting of the inclusions when composed together. So if I have V double prime, a subset of V prime, and that a subset of a big V, then I get the following diagram where I can restrict down to V prime in one step, or I can restrict down to V prime in two steps, and I want that diagram to commute. So if I restrict in one step, the same thing as if I restrict in two steps. And I also, yes, sir?
I have a question concerning this Presheaf construction. In principle, Presheaves are defined on Grothendieck topologies. So do those form one? Can one give those the structure of a Grothendieck topology, those commutative subalgebras?
So there has been some consideration of that. In particular, what is it? Landsmann's work, which is more topos theoretic specifically, looks at the topology given by upwards closed sets. And that turns out to be helpful when considering the internal version of a lot of what I'm saying today. I'm not going to be able to say much about that, but essentially what happens is you consider all of the Presheaves on this category at once. You consider that category with the Grothendieck topology of upward closed sets. And you look at the topos of all the Presheaves. And in that case, you have a sort of obvious, silly kind of Presheaf where you assign each commutative subalgebra to itself as a set. And then internal to that topos with that Grothendieck topology, the sheaves end up, the category of sheaves has an internal commutative C-star algebra object, and there's an internal Gelfand spectrum. And actually, most of what I'm saying today can be rephrased in that internal language, but I'm not as well versed in that as I should be. Yeah, but good question. Yeah, so for today, I'm not even going to be considering any topologies, actually. Okay. So that is a Presheaf in this specific case of a Presheaf on this context category. Okay. So in relation to the Kochen-Specker theorem, I have the following Presheaf specifically. Okay. So what I do is, let's see. So given A, commutative unidal C-star algebra as above, I'm going to define a Presheaf's big sigma from the, oops, I accidentally put two T's or two C's in there for some reason. Okay. From the context category of A, contravariantly, so I'll put an op up there to set. And this is exactly the same as the sigma notation I used earlier. That is, for a V in that context category, I'm exactly going to assign sigma V to be that Gelfand spectrum, all the characters. And that's why big sigma is used for this. S for spectrum. And for my inclusions, my corresponding restriction is going to be just like it sounds like. It's going to actually be the literal restriction where I take a lambda character on V and I just restrict it down to V prime. Okay. And we call this the spectral presheaf. So this idea here, this idea to consider everything in relation to a spectral presheaf, this arose from the work of Isham, Butterfield, and Hamilton. They, while studying the Kochen-Specker proof and some related things, they realized, okay, what have we literally said here? Well, we've said that this presheaf fails to have any global elements, any global sections. So let me see what I mean by that. When we have presheafs, we can think about them as sort of just like varying sets. That's a very natural way to look at them. It's a set varying over some base. So we have a natural notion of elements of this sort of varying set. So if I'm given some subset, let's say, of the contexts, and I'm going to require that subset to be downward closed, I can talk about having an element relative to just that subset. And we call these elements the sections of my presheaf over that particular subset. Okay. And this is really just a compatible choice of elements from all the different sets. Okay. So it is for each of my contexts that I picked from my little set, it's an element. In this case, a character from that particular commutative subalgebra. And they're compatible in the sense that whenever I take a subalgebra of V, if I look at my element lambda sub V that I had picked out in my section and restrict it down to V prime, I get the exact same element I had already picked out for V prime. So this is just a natural compatibility condition. It's just a natural way to pick out an element from not necessarily every one of my contexts, but at least a reasonable family of them, and also have all the restrictions and have everything be compatible. Okay. So with this, we can rephrase the Kochen-Specker theorem. Originally due to Isham et al. Okay. So in this rephrasing, we can say for A equals B of H, where again, the dimension of H is at least 3. The spectral presheaf has no global sections, meaning a section where I take my script V up here set to be all of the contexts at once. Yeah, so that spectral presheaf having no global sections, that is a natural rephrasing of the same thing, because as we observed above, okay, a global section would correspond to a valuation. because I would have a choice for every single self-adjoint element. Whoops, scroll down a little too much. Okay. So that's the reformulation that Isham, Butterfield, and Hamilton found that sort of captures the contextuality component very naturally by considering the compatible context directly with their post-set structure. So as before, we just said, okay, well, for this algebra, we just don't have any of these valuations. But it's very natural to say, okay, well, we have valuations in certain contexts. Why don't those extend globally? And this is the correct language to do that in. Okay. And maybe just a quick note on how to generalize this. I'm phrasing everything in terms of C-star algebras, mainly because I don't know a lot about von Neumann algebras and all the particularities, but it might be worth noting for people who are interested that this does generalize to von Neumann algebras. As long as they don't have factors of type 1 or type 1,1 or type 1,2, i.e. bounded functions on C or bounded functions on C2. So this is just my generalization of my requirement that my dimension is at least 3. Okay. But I'm not going to say much more about that. I'm just going to note that for anyone who might be interested. Okay, but this sparked a sort of general research line of people considering things relative to the context category of whatever algebra of observables was relevant. Okay, and this was sort of a new approach. And it led to a lot of different paths, but what I'm going to focus on is the extension of this due to Abramsky and his collaborators. Okay, so what we can do is give a general sheaf theoretic formulation of these measurement scenarios. And so that's what I'm going to do now. So what we do is we say, given a set X of measurements, okay, or maybe measurement labels, you might think of them with a discrete topology. Okay, and given a cover, and usually I require that cover to be an anti-chain, which means that none of the open sets in the cover are strictly contained in each other. That's not extremely necessary, but it is a little helpful. And in general, we mainly care about the sort of maximal context. So an anti-chain cover, which I'll denote M, consisting of some sets that I will think about as being as being compatible measurements. An anti-chain cover of, we'll think of these as the appropriate measurement context. So for Kochen-Specker, this is the commutative subalgebras. Okay. We have a set O of outcomes, which for everything I'm considering today is just the set 0, 1. I'm mainly only concerned with projections. Okay. Then we have all the possible assignments that one could potentially do. Okay. So I get a presheaf that I'll call the event sheaf that takes any old subset of X and maps it to all the possible functions from that set to O. Just any possible way of assigning things regardless of any compatibility considerations at all. And whenever we're considering one of these, we're considering it in relation to a so-called empirical model, by which I mean a family E where I'm indexing by the, sorry, not all of the context, just indexing by the cover. Where each of these is a probability distribution on that subset. probability distribution on that particular context C. And lastly, I consider the support of that probability distribution. Really, I consider it as a sub-presheaf. So that means I'm really going to, for each set U, take the set of all possible events, but restrict down to the ones that land in the support of the relevant probability distribution. Okay, so this is the setup I'm going to use. I've got possible measurements, such as, for example, all the projections or all of the self-adjoint elements. I have a cover consisting maybe of all of the commutative subalgebras or some particular commuting subalgebras. I have all of my possible outcomes and all of the possible events where I assign a measurement to an outcome. And I have a probability distribution that tells me which ones are possible and which ones aren't. And that's why I'm restricting to the support here. I really only care about which ones are possible right now and which ones aren't, not which ones have certain probability, just as long as they have non-zero probability. Okay. So this is the approach that Abramsky et al. Set up. We've already seen sort of one example, but let me give some conceptually simpler examples. This one is known as the Kochen-Specker triangle. And it illustrates just sort of how the theoretical setup goes pretty well. Okay, so in this case, I'm only going to consider myself as having 3 measurements I care about. I've got 2 possible outcomes for each measurement. And in this case, I'm going to take my measurement cover to consist of all the pairs, AB, BC, and AC. So the idea is that I'm only ever able to compatibly measure 2 of these at a time and never measure all 3 at once. Okay? And the empirical model I'm going to consider, I'm going to fill out in this table. So for each row here, I'm going to put AB, BC, AB. Those are my different measurement contexts. And I'm going to consider the possible ways I could assign those to any values. So up here for the column headers, I'm going to put all the possible elements in the event sheaf. So 0, 0, A is 0, B is 0, 0, 1, A is 0, B is 1, 1, 0, and 1, 1. Okay. And we're going to consider this scenario where it's impossible to ever find the same value with your measurements. And instead you find that no matter which pair of measurements you pick, that you always get opposite values. Okay. This is an example where the contextuality is sort of obvious. If I pick any one of these elements in this table, for example, maybe I pick this one right here in this box. Okay. This represents a restricted little section that assigns my context A, B, I should say assigns A to 0 and B to 1, but only on the restricted context AB. Okay. And the same thing for all these other ones in the table. They indicate a place where there is actually a section, at least in the support of this relevant model. Okay. But there's definitely no global section. And it's, again, not too hard to see that. Because if I pick a 0 for one and a 1 for the other, but I haven't allowed any duplications when I measure 2 at the same time, I've never allowed A and B, B or C, or AB to be both 0 or both 1, then as soon as I try to pick a second measurement, I run into a conflict. If I pick this one where I assign A to 0 and B to 1, as soon as I try to pick a value for C, it's going to match with either A or B, and that's disallowed by my table. Okay, so I'm still in green, I guess, but too late to change. Clearly, there is no global section. And there's a nice way to picture this by drawing what's called a bundle diagram. So what I'll do is make all of my different possible measurements vertices, connect them with lines when they're compatible, and above each one, put the two possible values, 0 and 1. Okay. And every time I have something in the section, for example, AB being assigned 0, 1, I can draw a little line connecting the fibers, so to speak, above A and B at 0 and 1. But the way this table is set up, I can connect any two of them with, so to speak, diagonal going assignments. Okay? And I end up with this. And if I follow this around from any one particular spot, if I go from 0 down here to 1, 1 back up to 0, 0 back over to A, I don't wind up back where I started. I immediately hit a contradiction here. And so this sort of visually shows that contradiction. I can start at a point A, try to complete a path. I end up back at A, and I don't really end up back at the value I started with. Instead, I have to go all the way around and change all of my values to get back to the value I started with. Okay. What we'll say in this situation is that this model is strongly contextual. And what I mean by that precisely, strongly contextual means that no section can be extended. Sorry about that. No section can be extended globally. Okay? So this is the same phenomena we saw in the Kochen-Specker proof. This is just a much simpler example. Okay. So Sampson and Abramsky and his collaborators moved on from this to consider, let me show the bundle diagram actually, to consider ways in which cohomology could answer questions about contextuality and to what extent it could be used to detect contextuality. Okay. Maybe I won't write up all the formalities. Maybe I'll just write this note, okay? So, Abramsky et al. Consider the Zec cohomology given by taking free abelian groups on my support. This seemed like a promising route to go. And it actually does successfully detect contextuality in a lot of cases. In particular, what we find is that if there doesn't exist a closed loop in this bundle diagram that starts and ends at the same point, only touches each vertex once, a simple little walk through that graph, then the first cohomology group doesn't vanish. So there are cohomological witnesses, so to speak, to this non-contextuality. But this formalism, unfortunately, it was found, does not always successfully detect the contextuality. And there's a simple example where this fails to hold. And this example will also let me at least explain a little bit how the Zec cohomology comes in by looking at how it fails to account for the contextuality in this Hardy model. So this Hardy model is going to consist of 4 measurements. And I'm going to label them A, B, A prime, and B prime, because the idea is that A and A prime can't be performed at the same time, and B prime can't be performed at the same time. We sort of imagine that there's an Alice and a Bob, and they each have 2 measurements they can perform, but they can only perform one at a time. So my measurement contexts are going to consist of all the other pairs. A, B, A prime, B, and so on, but never A prime, never B, B prime. Okay. And the following support table witnesses a form of contextuality that is not detectable cohomologically. So, just like before, I've got my context on the left, I've got the possible events up top, and I'm going to put a 1 if that event is possible and a 0 otherwise. So, for this model, the only things that are disallowed are A and B prime and A prime and B being both 0 at the same time. That's these two zeros in the far left column. And A prime and B prime both being 1 at the same time. Okay? So this model, that yellow is not showing up. Let's do this. Let's focus on this first section. I'll call it S1 up here. This section S1 does not have an extension to a global section. And that's not too hard to see, because if it did have an extension, okay, it would have to assign A and B to 0, but it's not possible for A and B prime and A prime and B to both be 0, so it would have to assign one of them 1, and in fact, both of them would have to be assigned 1, but then down here in the bottom right, we said, oh, that's not allowed, okay? But if we construct the bundle diagram for this, and consider what happens in cohomology, in particular, we just need to consider what happens when I take the free abelian group on my sections, we'll see that the cohomology actually fails and necessarily has to fail to detect this contextuality in this form. So I'll set up a similar diagram. In fact, I might need to move this down a little ways. Let me give myself some more room here, but still have the model showing up. Okay. So above A, I've got two options, 0 and 1. Above B, I've got two options, 0 and 1. Likewise for B prime and A prime. So 0, 0, 1, 1, 0, 0, 1, 1. Okay. Well, this section here that I've outlined, 0, 0, connecting A and B, right here. And let's see. Let me go ahead and fill in the rest of the chart with green. So the only things that are disallowed are A and B prime and A prime and B being both 0, 0. So for example, my A prime B on this back, I can't connect 0, 0, but I can connect 0, 1, 1, 0, and 1, 1. So I can connect there, I can connect there, and I can connect there. And the same thing's true of the front up here. I can't connect those, but I can connect all of these. However, I can connect all of these just fine. Except I cannot make A prime and B prime both 1, which is the last one I drew. I can connect those just fine. And I can connect these just fine. Okay? So, following the same track as before, starting here trying to include this path, if I walk around, I see that I can't find any consistent path that allows me to wind back up at 0 and 0 for both A and B. Okay? But once we take the free abelian group and we allow chains of these, sort of pseudo-compatible family shows up. Because this section over here, I'll call this S2, that one doesn't exhibit contextuality. So if I assign A and B 1 and 1, there's a perfectly valid path that assigns these 1 and 1, 1, 0, 1, 0, and 0, 0. And when I allow myself to take chains, when I allow myself to take linear combinations, I end up, so to speak, creating a path that connects this section here with this other chain that did indeed represent a proper compatible family. So it was determined that there were, so to speak, false negatives in the cohomological formulation. Okay. And that's sort of where the state of things is right now. The open question is how to refine to detect contextuality always. Okay. There's been progress on this. And so I'll just note the work of Giovanni Caru, one of Abramsky's students, in 2019, in his thesis, determined that higher cohomology groups don't work, don't suffice, and instead further refinement is necessary. Okay? But there is sort of a sunny spot in that these methods do detect contextuality in the majority of cases. And in particular, they do detect contextuality in, I'll just say, all known realizable models, by which I mean models that can actually be at least theoretically designed as a quantum mechanical thought experiment. This Hardy model that we just saw failed to have its contextuality detected is not actually realizable in any quantum mechanical scenario. We can't actually set up, for example, 2 qubits entangled in such a way that these probabilities, or at least these supports of probabilities, are possible. So this is sort of the state of things right now with the cohomological and sheaf theoretic approach. The higher cohomology groups, as they are, don't always detect contextuality in the broadest sense of contextuality, but they have been shown to detect contextuality when we consider actual quantum mechanical scenarios. So that's good. But there is sort of, how should I put this? What am I trying to say? There's still plenty of room to try to figure out where the gaps are. In particular, my understanding, and I might be wrong about this, is that there isn't a formal proof that every quantum mechanically realizable model has its cohomology detected. I believe that's open. Let's see, how much time should I have? We started a little bit late. So
it's about to end, so maybe.
Okay, so yeah, maybe I'll just end there. I was maybe going to say just a little bit about the topos theoretic approach, but I already pretty much mentioned everything when I answered Marcus's question earlier. So I think I'll just end here and open up for any questions.
Yeah, let's first thank the speaker for the nice talk. Please open your mic. Yeah, and now questions. So in addition to the question you already answered, I mean, in principle, there are other, let's say, algebraic topological methods besides homology and cohomology one could think of. Are there ideas to use those, or does that even make sense?
Yeah. So in Giovanni Caru's thesis, he explored refining this by using valuation algebras. Essentially considering a situation where you're not looking at a single section at once, but you're looking at the neighboring sections as well, and trying to sort of refine that way by sort of like adding on a section at a time. That's the approach that Giovanni Caru took in his thesis, and he was able to show there a much more refined invariant of contextuality. It was able to detect contextuality in all of the empirical cases, at least, that we've talked about here. Sort of where my headspace is with this, especially when considering Caru's approach that, like I said, refines by considering adding more and more sections, is that perhaps homology would still be useful if we consider it persistently, and if we consider maybe refining the approach that we take to define the covers, where maybe we getting a little hand wavy now, but where the persistent homology maybe is tracking pairs of sections and then triples of sections and things like that, so that you're kind of building up the sections persistently, if that makes sense. I don't know. That's just sort of a hand wavy idea where my head's been going with it, but yeah.
Okay. Further questions? Okay, then let's thank the speaker again.
Go ahead and stop sharing.
And